Now let us look at one-dimensional wave equation. So we have already discussed in the class one-dimensional wave equation and its derivation. So I'll quickly go through one-dimensional wave equation now because it is very important to know the derivation as well as the general solution. Okay, for this we consider a tightly stretched elastic string of length L which is fixed in the endpoints A and B, and we have given a constant tension T. Tension is considered to be large so that mass of the string and gravity is negligible. Okay, the string is first of all released and allowed to vibrate. Okay, so we study the subsequent motion of the string with no external force acting on it. That means the force acting on the string is only due to the tension as well as the tension, and also we don't consider any other forces acting on it. Okay, so now we discuss the vibration of the string from the equilibrium position AB, and we try to find the displacement of the string at any point at any time t. For this we first of all draw this diagram. The string is attached at both ends A and B, and we have chosen 2 points P and Q on the string, and as we have discussed, we apply constant tension T. So tension is applied on both P and Q and it is constant. We call that as a tension capital T, and it is acting on the point P and Q. So we derive the solution for this particular portion first of all. Okay, so suppose that the distance between P and Q is delta x, and now to derive we take a point P and we draw a line parallel to x-axis from P. Also we draw a line parallel to x-axis from Q, and we call an angle psi from this tension to the parallel line, and psi plus delta psi from the point Q, the line drawn parallel to x-axis and tension T. That means at a point P we have an angle psi, at a point Q we have an angle psi plus delta psi. Okay, so the point P is ordered per xy, that is x value is x and y distance is y, and the point Q is ordered per x plus delta x, y plus delta y, that is the x value is x plus delta x and y value is y plus delta y for the point Q. And subsequently we know that the angles are psi and psi plus delta psi for P and Q respectively. Okay, now we derive the wave equation, first of all taking the aspect that uniform tension is applied on the string and the tension is only the force acting on the string. Okay, so we try to derive, first of all find the horizontal and vertical component, compare the horizontal and vertical component. For the present situation we only take the sine component, vertical component. Okay, so sine component, that means we have discussed this in the class also. If we have an angle, a force acting on some point, say this is a force, and if we have an angle psi, we can say that sine psi is equal to opposite side, this side, divided by, we can call this force. Okay, we can call this force. Okay, we can see that in this picture we can consider the vertical and horizontal component. Okay, so we can have vertical component as well as horizontal component. So this vertical component, we can say this is a vertical component. Okay, so F vertical is a vertical component and this is horizontal component. So clearly sine psi is equal to force on the vertical component divided by the actual force. Okay, also we can say that F into sine psi is equal to force in the vertical component. So we can say that here tension is the force acting. Tension into sine psi is equal to force on the vertical component. So if we consider only the force in the vertical component, we can take for the point P, we can take it as T sine psi, and this can be T sine psi plus delta psi. So the difference is T sine delta psi, psi plus delta psi minus T sine psi. So we can take T outside, we can say that it's equal to T into psi plus delta psi minus sine psi. Also for the small angle, we can say sine is almost equal to tan. Sine theta is almost equal to tan, because sine theta is equal to or tan theta is equal to, we can say that sine theta by cos theta. For small angle, cos theta is 10 to 0, theta is 10 to 0, then cos theta 10 to 1. Therefore it is almost equal to sine theta. Tan theta is almost equal to sine theta for small angle. We suppose that the deflection is very small, so we can convert, we can even take, instead of sine theta we can take tan theta or tan psi. Here we can take, instead of sine psi plus delta psi, we can take sine tan psi plus delta psi. Okay. Also we have discussed this also. We can take tan of the angle as derivative point. Okay, derivative at point. So here we can take dou y by dou x at the point x plus delta x, and this can be dou y by dou x at point x. Okay, so we keep this thing and we move forward in the other direction. So suppose this force, by taking from the Newton's second law, we can say that force is equal to mass into acceleration. Here we have discussed, or we have taken mass as unit mass as small m, and the distance as delta x. So total mass on the particular position PQ is, particular portion PQ is m into delta x, and acceleration is dou square y by dou t square. So this is the force acting on the string by according to Newton's second law. Okay, we have also have, by using the tension and vertical component, this side we have, this is the force. Okay, we can equate these two. So we can equate m delta x into dou square y by dou t square is equal to t into that term that we derived in the previous slide. Now we can take dou square y by dou t square one side, and we can take other parts, other variables in the other side, and rearrange, we get this. Okay, so also we have this particular portion, we have a change in a variable, divided by the cos of a change, limit, when you apply limit 10 to 0, delta x 10 to 0, if it is delta x, the change in function on delta x, and divided by delta x, as delta x 10 to 0 is the derivative. So for this we can say this can be, or this we can take as second derivative dou square y by dou x square. Okay, dou square y by dou x square. So comparing these two, we can say that dou square y by dou t square is equal to c square into dou square y by dou x square, where c square is, we put t by m, capital T by m. So this is the one-dimensional wave equation. Okay, now we can first of all find the solution of one-dimensional wave equation. For this we use method of separation of variable, and first of all, since this y is the dependent variable, and we have x and t as independent variables, so we can say that y of xt will be the solution. So suppose that is equal to capital XT, where x is only function of x and t is only function of small t. So by taking that into account, we can take we can find different partial derivative, that is dou square y by dou t square is equal to xt double dash, and dou square y by dou x square is equal to x double dash t. Okay, we can substitute all these in the one-dimensional wave equation. Dou square y by dou t square is equal to c square into dou square y by dou x square. So we can substitute this and rearrange. So what we get is xt double dash is equal to c square into x double dash t. Okay, so moving this variable, we can divide by capital Xt. What we get is t double dash divided by t. We can take c square also this side, equal to x double dash divided by x. Suppose that this is equal to some constant k. That means x double dash by x is equal to some constant k, and t double dash by c square t is equal to some constant k. So what we do is we try to solve this now. So this is first derivative. It's a typing error. Okay. So we develop two equations. That means x double dash by x is equal to some constant, and t double dash divided by c square t is equal to some constant. We can move this variable, that we get x double dash is equal to k into capital X. Similarly, t double dash is equal to c square t into k into t. So we actually have x double dash is equal to d square x by dx. Okay, dx square. So taking this in account, we can convert this as two equations. One is this and other is this. We can call this 3 and 4. Okay, 3 and 4, equation 3 and 4. By solving this equation 3 and 4, we will get the variable, or we will get the function y of xt. Okay, for that we take three things. That is, we have received differential equation d square x by dx square small x square is equal to or minus what we get is, in the previous slide we have e minus k x is equal to 0, and d square t by dt square minus c square k t is equal to 0. So this k can be either positive or negative or 0. So we take three cases. K is equal to positive, for that we take k equal to p square, k is negative, k equal to minus p square, and k equal to 0. These three cases we take. Okay, so first of all, when we take k equal to p square, I will solve this in the bottom. Okay, for k equal to p square, we can have that d square x by dx square minus p square x is equal to 0. Okay, we can convert this into auxiliary equation m square minus p square equal to 0. That means m square equal to p square, therefore m is equal to plus or minus p. Therefore we get two different cases. So these are two individual or two different real roots, so that we can take equation of, or we can solve this value as x is equal to c1 e raised to px plus c2 e raised to minus px. Okay, now for other differential equation, d square t by dt square minus c square k t is equal to 0. We take auxiliary equation m square minus c square p square equal to 0. That is, m square equal to c square p square. So m is equal to plus or minus cp. Okay, in that case we can take t is equal to c3 e raised to cp x plus c4 e raised to minus cp x. Okay, so these two we get. So for ultimately we can take the solution as xt is equal to y of xt is equal to c1 e raised to px plus c2 e raised to minus px into c3 e raised to cpx plus C4 e raised to minus Cpx. Okay, now we have to take another case. Instead of x we take t here, right? Cpt. Okay, so ultimately what we get is this solution. Now we have to take another case for k equal to minus p square. Okay, that we have k equal to minus p square, so what we get is m square plus p square equal to 0, the auxiliary equation. Correspondingly we get m is equal to plus or minus pi. For this we can solve. X is equal to c1 cos px plus c2 sin px. Similarly for other variable, for t we can say that m square plus c square p square equal to 0 implies m is equal to plus or minus cpi. For this we can choose other solution, that is capital T is equal to c3 cos cpt plus c4 sin cpt. Okay, for this the xt becomes y of xt is equal to capital Xt is equal to c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. Okay, similarly we have taken k is equal to minus p square, k is equal to p square. Now we take k equal to 0. Okay, then the differential equation becomes d square x by dx square equal to 0. That means x is equal to c1 plus c2x. For the variable t, d square t by dt square equal to 0. Therefore t becomes c1 plus c2t or c3 plus c4t. Okay, therefore y of xt is equal to capital Xt is equal to c1 plus c2x into c3 plus c4t. So we have three solutions. We received three different solutions for different p. That is, one is y of xt is equal to c1 e raised to px plus c2 e raised to minus px into c3 e raised to cpt plus c4 e raised to minus cpt. Second is y of for k equal to, this is for k equal to p square. For k equal to minus p square we have y of xt is equal to c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. And k equal to 0 we have y of xt is equal to c1 plus c2x into c3 plus c4t. Of these solutions, this only solution is of physical nature, very similar to physical nature. That is, the problem when we try to do this problem in the real situation, experimental setup, only this solution is very similar to the solution of case when k equal to minus p square. So we take this as the general solution for one dimensional wave equation. Okay, so we take this as general solution for one dimensional wave equation. So this is the general solution for one dimensional wave equation. Now since we have a string which is vibrating, and we are trying to measure the deflection or displacement of the string which is vibrating, y of xt. Okay, x is for position of the string and t is for the time. Okay, so we can have, when x equal to 0 and x equal to the length of the string, okay, we can have different conditions. For example, y of 0t, which is at position 0, since from the assumption itself we have the string is tightly fixed at the endpoints, this becomes 0. Okay, similarly y of lt, here also since the string is attached at the endpoints, we can say that this is equal to 0. This is called boundary conditions. Okay, now also we have uh, the initial position of the string, y of, we have y of xt, we can put t equal to 0, that means y of x0 is called the initial position of the string. This can be also an input to the specific problem. Also, initial, if you take the initial position and its rate of change, which is called initial velocity, this also can be a input to a particular case. So based on these these four input, that is two boundary condition and two initial condition, that is one initial condition is initial displacement and second initial condition is initial velocity. So these four conditions contribute to the problem or contribute to the solution of partial differential equation of one-dimensional wave equation. That means to solve one-dimensional wave equation, we have to find the constant C1, C2, C3 and C4 to solve it completely. For that we use the inputs like boundary condition and initial conditions. That is, these four conditions we have to input for finding values of constants. Okay. Now we have an important principle called principle of superposition. This is nothing but we have different solutions for one-dimensional wave equation. U1, U2, U3 and U4 etc. are the solution. Then its linear combination is again a solution. Okay, so that means C1 U1 plus C2 U2 plus etc. CK UK is again a solution. This is called principle of superposition. Now we are in position to solve or find a complete solution of one-dimensional wave equation. So now let us solve this. This is a particular example. Okay, so now a string is touched and fastened. It is tied on two endpoints and the distance between these is L. The question gives it is fastened at 2 points L apart. Motion is started by displacing the string from a sine pi x by L. So motion is started by displacing a string from this position. So we have tightly cast this and it is released at a time t equal to 0. Okay, we have to show that the displacement of any point, the solution is a sine pi x by L into cos pi ct by L. Immediately after getting this kind of problem, we have to think about the conditions. We have to input, first of all we have to know that the general the wave equation, one-dimensional wave equation is dou square y by dou t square is equal to c square into dou square y by dou x square. Okay, so we have to find the cases of p's. So p equal to k equal to p square, k equal to minus p square and k equal to 0. So applying this, we get the general solution is y of xt is equal to c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. Also we have received this kind of solution because we have put the initial condition. Like the initial conditions are, since the string is tightly structured at, or fixed at the endpoints at x equal to 0 and x equal to L, we have the values. That means y of 0t is equal to 0 and y of Lt is equal to 0. Also in the problem it is given that it is motion is started by displacing the string from the position. Okay, here it is given that motion is started displacing the string from some position, so that initial position is given. So that initial position is given, we can say that initial position means t equal to 0. That means y cx0 equal to some value which is given as sine pi x by L. This was given. Okay, also since it is given that it is released at time t equal to 0, that means it was not moving at that time when t equal to 0. That immediately gives that dou by dou t of y of x0 equal to 0. That means initial velocity is 0. That may, for all together we can say that in this problem what are given, this problem reduces to y of 0 t equal to 0 and y of Lt equal to 0 and initial displacement y of x0 is equal to as sine pi x by L and initial velocity dou by dou t of y of x0 equal to 0. Actually, whenever you get try to solve a problem in wave equation, you have to find all these points from the statement. Then immediately we say that the wave equation, one-dimensional wave equation, is dou square y by dou t square is equal to c square into dou square y by dou x square, and we can write the general solution y of xt as c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. Okay, now what we need to do is we need to input all these conditions one by one to receive the general solution. That means we need to input the first condition first. Okay, so we first of all input the first condition, y of 0t equal to 0. Okay, y of 0t equal to 0, we put that in this particular equation. So what we get is 0 equal to, we put instead of x we put 0. That means c1 plus c2 into 0 into c3 cos cpt plus c4 sin cpt. Okay, this is 0. Since from the first point, this point we can say that this point we can say that this is equal to 0. So we have x into y equal to 0 means either x equal to 0 or y equal to 0. Here either of this quantity need to be 0. So only possible, if this point were 0, this quantity were 0, what happens? Always this solution will be 0. So only possibility is c1 equal to 0. Otherwise what happens? If the second factor is 0, always we get y of xt equal to 0. So only possibility is c1 equal to 0. Now we what need to do is we substitute this c1 equal to 0 in this particular general equation and revise the equation. Okay, this is very important point. We need to revise the equation y of xt equal to, substituting c1 equal to 0, c2 sin px into c3 cos cpt plus c4 sin cpt. Okay, we revise the solution. Now we can apply any of the condition as you like. Okay, so I first of all apply the second condition. Second condition is y of Lt equal to 0. That means we substitute this in this particular. This is a revised solution. We can call it 2. Okay, so we substitute these values in this equation. What we get is 0 equal to, instead of x we put L, c2 sin pl into C2 sine PL into C3 cos CPT plus C4 sine CPT. Okay, C3 cos CPT plus C4 sine CPT. Okay, now there are two conditions. We have already C1 equal to 0. If C2 is also 0, what happens? The solution will always become 0. Okay, therefore C2 cannot be 0. Then this quantity can it be 0? No. This, if it is 0, the situation repeats. That means this all the term will become 0. So only the cases where sine PL equal to 0. Okay, sine PL is not always 0. You know this graph of sine. So sine PL is not always 0. It can create a wave. That means PL is equal to n pi. That is P equal to n pi by L. Okay, P equal to n pi by L. So we go back to this particular solution. So we revise the solution again by substituting P equal to n pi by L. So our new y of xt equal to C2 sine, instead of P, n pi by Lx into C3 cos n pi by L into Ct plus C4 sine n pi by L into Ct. So this is the solution. Now what we get there? This is the solution. Now I take other case where we can try next stage. That means dou by dou t of y of x0. It is given that it is equal to 0. So we substitute this. First of all, we find the derivative of this particular thing. That is dou by dou t of y of xt. We find wherever you find t, you need to find the derivative. Okay, C2 sine n pi by Lx into C3 into the coefficient of t, n pi by L into C into derivative of cos minus sine n pi by L into C into t plus C4 into n pi by L into C into cos n pi by L into Ct. But it is given that dou by dou t of y of x0 equal to 0. So we find dou by dou t of y of x0. We put t equal to 0 in this. So what we get is C2 sine n pi by Lx into, we put 0, what we get is 0 into C4 n pi by L into C into cos n pi by L into Ct. Okay, that means this quantity should be 0. So the next only possibility for this is, we can write like this: C2 C4 into n pi by L into C into sine n pi by Lx into cos n pi by L Ct. Okay, this means either of this quantity can be 0. Only possibility here is we can put C2 C4 equal to 0, but if C2 is again 0, C2 is 0, this quantity all becomes 0. So only possibility is C4 equal to 0. At least we can get some values for C3 in that case. So we put C4 equal to 0 and replace this particular red. I mark this as red. So we go to back to solution and replace that. So y of xt becomes C2 sine pi n pi by Lx into C3 into cos n pi by L Ct. Okay, we put as C2C3 into sin n pi by Lx into cos n pi by Lct. Okay, this is the case. So our new y of xt becomes this. Now we put the final case. Okay, final input, that is initial deflection, which has given that y of x0 is equal to a sine. In the question, we can see the question now, a sine pi x by l, which is given as marked as this thing, a sine pi x by l. We can put that a sine pi x by l. So when you put values for t equal to 0 in this, what we get is equal to C2 C3 sin n pi by Lx into cos 0 1 1. This immediately gives C1 C2 C3 equal to a. Okay, comparing the coefficients, C2 C3 equal to a and n equal to 1. Okay, so now put that back, y of xt now become C2 C3. Instead of C2 C3 we can write a sin n, instead of n we can write 1 sin pi x by l into cos pi ct by l, which was asked in the question, a sin pi x by l into cos pi ct by l. This is how we solve the equation. Okay, you can revise the equation. I will send the slides so you can compare and study that. What you need to do is you complete this proof and send to me for the link I upload. Okay, I will give a link in the WhatsApp group. You upload your answers to the link.